All right, let's dive in. Today, we're talking about the invisible forces that are basically running the show behind the scenes in our world. From the weather to our own bodies, we're uncovering the hidden rules of fluids.
So let's start with a classic puzzle, one you've probably wondered about since you were a kid. How in the world can a massive 200-ton ship made of solid steel just bob around on the water when a tiny little pebble sinks straight to the bottom? It just doesn't seem to make sense, right?
Well, it's not magic, it's physics. The answer is locked away inside a really cool field called fluid mechanics. These are the powerful and, a lot of times, invisible principles that tell liquids and gases what to do. So today, we're going to pull back the curtain and see how it all works.
But before we can even get to floating and sinking, we've got to take a step back and ask something even more basic. What exactly is a fluid anyway? I mean, think about it. Honey and mercury are both liquids, but they act completely differently. Honey is, well, it's lazy, it's thick, it clings to the spoon. But mercury, it's the total opposite. It's so dense that it pulls itself into this tight little sphere that can roll around. That difference is our first big clue.
The reason honey is so slow is because of a property called viscosity. The easiest way to think about it is just as a fluid's thickness, or its internal friction. The more viscous it is, the more it fights against flowing. It's basically a measure of how much the fluid's own molecules are dragging against each other.
Okay, so what about the mercury bead? For that, you need to understand these two competing forces, cohesion and adhesion. It's pretty simple. Cohesion is how much a fluid's molecules want to stick to each other. Adhesion is how much they want to stick to other things, like the glass they're in. With mercury, cohesion is incredibly strong. The mercury molecules would much rather hang out with each other than touch the glass. That's why they form that tight ball. Water is the opposite. Adhesion is stronger, which is why you see water kind of climbing up the sides of a glass.
Okay, so fluids are sticky. They can flow. Got it. But there's another huge piece to this puzzle. They're heavy. And the weight of a fluid, even when it's just sitting still, creates a ton of force. This is all about fluid pressure. Let's picture this. You've got a big tank. It's filled with 10 meters of water. That's over 30 feet deep. Down at the bottom, there's a gate. How much force do you think is pushing on that one gate? Just take a guess.
The idea at work here is called hydrostatic pressure. And simply put, it just means the deeper you go, the more water is sitting on top of you, and the more weight is crushing down. Gravity is pulling on all that water, so the pressure goes up and up the farther down you are.
So how do we figure it out? First, we find the average pressure on the middle of the gate. Then, we just multiply that by the gate's total area. And the result is absolutely mind-blowing. 880,000 newtons of force. To put that in perspective, that's like having more than 13 full-grown elephants leaning against that one single gate, just from water sitting still. And you know what's crazy? That same incredible downward force is actually the key to solving our very first mystery. Because when that pressure pushes on an object from every direction, it creates an upward force. And that right there is the secret of floating. It's called buoyancy.
Let's play with this idea a bit. Imagine we have a 30-centimeter rod. Now, we know its density is exactly 75% of water's density. If you drop it in a pool, it's going to float standing straight up. So the question is, how much of that rod is actually going to be under the water?
The answer comes from probably one of the most famous aha moments in history, Archimedes' principle. All it says is that an object is pushed upward by a force that's equal to the weight of the fluid it moves out of the way. You see, floating is just a perfect balancing act. The object's own weight is pulling it down, and the water it shoves aside is pushing it right back up. And here's where it all just clicks. Since our rod is 75% as dense as water, it only needs to push aside a volume of water equal to 75% of its own volume to float, which means exactly 75% of its length will be underwater, 22.5 centimeters. It's just that simple and elegant.
But hey, just floating isn't good enough, right? A ship also has to be stable. This all comes down to two imaginary points, the center of gravity, which is where the ship's weight pushes down, and the center of buoyancy, where the water's force pushes up. For a stable ship, you want that center of buoyancy above the center of gravity. That way, if the ship tilts, those two forces work together to pull it back upright. If they're flipped, a small wave can be enough to make it roll right over. All right, so far we've just been looking at fluids that are sitting still.
But things get really interesting when they start to move. This is where we get into the rules of flow, from a perfectly smooth stream all the way to total chaos.
Here's one you already know the answer to, even if you don't realize it. You've done this 1,000 times with a garden hose. Water's flowing through the pipe, and then you put your thumb over the end, making the opening narrower. What happens to the speed of the water?
It speeds up, of course. This is all because of the continuity equation, and it's based on a really simple idea. What goes in must come out. You can't create or destroy water inside the pipe, so if you shrink the area it has to flow through, the velocity has to pick up the slack to keep the same amount of water moving through. It's like the universe's way of saying, nope, no traffic jams allowed here.
But not all flow is nice and orderly. There's this kind of magic number in fluid mechanics called the Reynolds number. It takes into account the fluid's speed, its viscosity, and the pipe's diameter. In a pipe, if that number is below about 2100, the flow is usually smooth and predictable. We call that laminar. But once you cross that threshold, things can get messy. The flow becomes chaotic and unpredictable or turbulent. So we've got all these pieces now: viscosity, pressure, buoyancy, flow. How do engineers actually take these hidden rules and use them to solve real problems? Let's walk through a classic engineering challenge.
Imagine you're trying to pump oil through a pipeline. That oil is viscous, right? So it creates friction as it rubs against the inside of the pipe. Every single foot of that pipe just sucks a tiny bit of energy and pressure out of the flow. So the big question is, how much pressure do you actually lose over just 1 mile of pipe?
Well, to solve this, an engineer has to pull out every tool we've talked about today. They'd use the continuity equation to find the oil's speed. Then they'd calculate the Reynolds number to see if the flow is smooth or turbulent, because that changes everything. They even have to account for how rough the inside of the pipe is. It's a true mashup of all these hidden rules.
And the final answer is pretty shocking. For a pretty typical setup, SAE 10 oil in an 8-inch pipe, you lose a massive 86.6 psi of pressure. That's for every single mile. That is a huge amount of energy that the pumps have to constantly fight against. And it shows you just how important these rules are in the real world.
So let's wrap this all up. What are the big hidden rules we found today? First, you've got viscosity. That's the fluid's inner stickiness. Then there's pressure. That's the incredible force from the sheer weight of a fluid. Third is buoyancy, the magic upward push that lets things float. And finally, flow, that constant dance between speed, space, and the edge of chaos.
These rules, they aren't just in some textbook. They're everywhere. You'll see them in how cream swirls in your coffee, in the way a plane's wing gets lift, in the design of a massive dam holding back a lake. So now that you know the rules of the game, my question to you is, where are you going to see them at work next?